Welcome to the lecture for section 14.3. This is MGF 1106, Liberal Arts Math, and my name is Jorge. So in this section, we're going to be talking about the measures of dispersion. In the previous section, we spoke about the measures of central tendency, and that, of course, was the mean, median, and the mode. In this section, we're going to be talking about the range, which is simply the largest minus the smallest value in the data set. And then we're going to be talking about the standard deviation and how the standard deviation measures a spread of a distribution. And then the last thing is we're going to talk about the coefficient of variation, and this is used to compare standard deviations for different distributions. So here, the first thing we're going to talk about is the range, and like we did in class last time that we met, the range of a data set is the difference between the largest and the smallest data values in the set. Now, the range is a crude measure of the spread of the data. And so it's crude because it doesn't really tell you a whole lot about it, especially if the high value or the minimum value is what we call an outlier, which is either extremely high in comparison to the other data points or extremely low in comparison to the other data points. You can have a really large range, but it can actually be a false reading, if you will. So here's the first example. We're going to find a range of the heights of the people listed in the accompanying table. So here we have 4 people. We have their heights, so in feet and inches, and we're going to convert that all into inches. And so now we can go ahead and find the range. And what we do is we take the largest data value, which is 102 inches, minus the smallest, which is 26 inches. So the range for this data set is 76 inches, which is equivalent to 6 feet 4 inches. Next thing we're going to talk about is standard deviation. So if x is a data value in a set that has a mean x bar, and if you remember x bar is the mean for a sample, then x minus x bar is called the x's deviation from the mean. So we have a table, and we have the data value 16, 14, 12, 21, and 22. And the mean for this data set is 17. So 16 minus 17 is negative 1, 14 minus 17 is negative 3, and so on. And you notice that if we add up all of these data values, the sum actually adds up to 0. So this leads us to the formula. And the definition, or the formal definition for standard deviation, the formula is of a sample of n data values by s is equal to the square root of the summation of the different squares, deviation squared, divided by n minus 1. N minus 1 is what we call degree of freedom, and it's outside the scope of this class, but it's done so it can be a better approximation. And so again, here you see the data value, so x, and then deviation from the mean, so that's the difference between the data value and the mean. Some are positive, some are negative, and if you recall, when we added those up, we got 0. So the reason why we square them is so they're all positive. That way, when we add them up, we actually get a positive value. So now we add up the deviation squares. We get 76. We divide them by 4 because we have 5 data values. 5 minus 1 is 4. And then that equals to 19. So then the answer would be the square root of 19, which is approximately 4.36. So the standard deviation for this data set is 4.36. So these are the steps in computing the standard deviation. So the first thing is we have to find the mean of the data set, and because we're going to be dealing with samples, it's going to be x bar. Then we go ahead and find the squared deviation of the data points from the mean, and we do that for each data point. Then we add up the squares, and then we divide by n minus 1. And this is the variance. So before we find the square root, the value that we get is the variance. And then we'll go ahead and get the square root of the variance, and we get the standard deviation. So here's an example. A company has hired 6 interns, and after 4 months, their work records show the following numbers of work days missed for each worker. And the data set is 0, 2, 1, 4, 2, and 3. So we're going to go ahead and find the standard deviation for this data set. So the first thing again is we find a mean, and we find a mean for this data set is 2. So 2 days is the average days missed. The next thing that we do is we're going to go ahead and find the deviation from the mean for each data point, and then we're going to go ahead and square the deviation from the mean for each data point, and then we're going to add those up. And the summation of that column is 10. So 10 divided by 5, because there's 6 data points, 6 minus 1 is 5, is approximately 1.41. So for this data set, the mean was 2 days with a standard deviation of 1.41 days. And the next thing we're going to talk about is computing the standard deviation for a frequency distribution. And we did this, we did something similar to this when we did a frequency table and we were trying to find a mean. So the first thing is we calculate the standard deviation as of a sample that's giving as a frequency distribution. Another thing that we call this is group data. So the formula for this one is the square root of the summations of the deviations from the mean squared times the frequency divided by n minus 1. Again, x bar is the mean of the distribution, f is the frequency of the data value for each particular x, and then n is equal to the summation of the frequencies, or the number of data values in the distribution. So here's another example. The following are closing prices for a stock for the past 20 trading sessions. So what is the standard deviation for this data set? And so the first thing that we do is we're going to go ahead and find a mean. So the mean is 40 for this particular data set. And then the next thing that we're going to do is we're going to go ahead and create a table. Actually, we should do this first. And then it makes life easier to find the information. So the closing price is the first column, the frequency is the second column, the x times the f is the third column. And of course, and if you notice, we have three values that we're going to need. So we're going to need the summation of the frequencies, we're going to need the summation of the product of the data value times the frequency, and then we're going to go ahead and need the deviation squared, the summation of the deviation squared times the frequencies. So, and that gives us 50. So what we have now then is the square root of 50 divided by 19. There's 20 data points, and 20 minus 1 is 19. It's approximately 1.62. So the next thing is we're going to go ahead and compare standard deviation. So in this slide here, we have three distributions, and they each have a mean and a median of 5. However, as the spread distribution increases, so does the standard deviation. So again, the first one, we have a standard deviation of 0.82. And if you can see that the bars are very tightly distributed. So the mean is 5, so they're really close. All of the data points are really close to 5. Now the second one, the standard deviation is 1.29. And as you can see, now they're a little bit more spread out. So they're not all clustered closely around the 5. Now we have some 3s, we have some 7s. And then the last one, the standard deviation is 2.38. And again, now you can see how the data set is actually even more spread out. So when you calculate the mean and the standard deviation for a data set, usually, let's say if the mean is 5 in this case point, and you have a really small standard deviation like a 0.82, then that means the data set is clustered around the mean, so it's really tight. But if you have a large standard deviation, so you have a mean of 5 and you have a standard deviation of 2.38, you should immediately know that it's very spread out. So the last thing we're going to talk about is coefficient of variation. So for a set of data with mean x bar and standard deviation s, we define the coefficient of variation denoted by capital CV. So CV is simply the standard deviation divided by the mean of the data set times 100%. So here we have two samples, right? So relatively speaking, there's more variation in the weights of first graders than NFL players. So the first graders have a mean of 30 pounds, standard deviation of 3 pounds. So 3 divided by 30 times 100 gives us 10%. So the coefficient of variation for the first graders is 10%. For the NFL players, we have a mean of 300, standard deviation of 10 pounds. 10 divided by 300 times 100 is 3.3%. So what happens when we find the coefficient of variation is that we're able to actually compare standard deviations for two separate data sets. And the reason we can't, you shouldn't go around comparing them is because a lot of times the units are different. Here, of course, we're talking about pounds and pounds, but coefficient of variation is just a better way to compare two data sets. So here's another example. So we're going to use the coefficient of variation to determine whether the women's 100-meter race or the men's marathon has had more consistent times over the 5 Olympics that are listed. So we have the women's 100 meters times. So it goes from 10.93 seconds to 10.54 seconds. And then we have the men's marathon, which goes from 7,855 seconds to 7,800. Actually, it goes to 8,003 seconds. So it's a pretty nice variation. So the first thing that we do is we find the mean for the 100 meters and the marathon. And then here we have the same units. You don't always have to have the same units, and that's one of the reasons why we use coefficient of variation. So standard deviation for the 100 meters is 0.163, for marathons 83.5. And then we get the CV for the 100 meters, which is 1.51%. The coefficient of variation for marathon is 1.06%. So using the coefficient of variation as a measure, then there's less variation in the times for the marathon than the 100-meter race. And that's the end of section 14.3. Thank you.